For our next part, we need to look at some more conceptual things about the phases of matter. So this should be mostly a review, and most of you know that we have 4 phases of matter, or at least you know of 3 of them. Solids, liquids, gases, most people get those all around. But plasma is our 4th level of matter, and you need to understand what it is too. And so we'll look at how these can exist. So basically, all matter and temperature even comes down to the kinetic molecular theory. And if you can break this word down, if you remember kinetic from our energy chapter, that's movement, right? So moving molecules theory, right? Now, all it really is stating is basically how much the molecules are moving depends on both their temperature and what phase they're in. That's why pressure can also result in it some, because if you think about it, if you push hard enough, things don't have room to move, and so they would have to be in something different. But first, let's think about temperature. Most of you think about temperature as it's hot or it's cold. Well, with temperature, it really is an average of all of the movement of those molecules. So as you increase in temperature, it means your average particle in that substance is moving faster. Now, if you think about this, in a solid, they're not moving very much at all. In fact, they tend to be a crystalline structure. If you add some energy or heat to it, you're going to move up those particles a little bit, and you might get a liquid of that. And this is seen with water very easily. So ice cube, very rigid. Add some energy. Now it can move around a little bit. They're free to slosh back and forth, but they're still bound, right? And then you add even more energy and more movement because of that energy, and you get particles moving all around, and you get a gaseous state. So now the particles can move all around the room. But if you energize it just enough more, these molecules will actually rip themselves in pieces into a positive and negative charge. And that's where we get to plasma, which is the final stage. So let's look at each one. Solids. You need to remember that particles vibrate, so they are somewhat moving. They're not perfectly still anywhere, but they can't really move around. They just can kind of vibrate in place. They're packed tightly together. They're very low on kinetic energy. They have a definite shape and volume. So that means volume is how much space it takes up. Shape is its actual shape, what it looks like, right? Now, there's basically 2 types of these solid molecular structures. There's a crystalline. Hear that word crystal in it? So it's a repeated geometric pattern. I like to think about it like this. If you've ever seen one of those lattice pieces of fence, you had pieces that are going that way, and then you had other pieces that are going that way. It makes a very definite shape, right? And a very definite pattern. Well, that's a crystalline lattice structure, meaning that if we had particles, like in a solid, you would see them a definite distance and shape away if you could zoom in on them, and they would be uniform in what they look like. That's a crystalline structure. Now, it doesn't have to be that repeated geometric pattern, but it's one like that. Now, amorphous is different. Amorphous is more sporadic. So now think about, let's say if you had sand at the beach, right? And you got a little bit wet and you mashed it in to make a sandcastle. Well, it doesn't line up all nice and neat. It just jams every particle tight together until it forms a solid. So it doesn't have a repeating pattern. It's still all together. Well, that's basically what glass and wax are. And that's also why if you drop a piece of glass, it doesn't break down into little squares. It breaks into, jagged pieces of glass because they're all packed in there odd. Now, liquids are next. They have the next highest, solids having the lowest of kinetic energy. So we're going to move up by the kinetic energy of the particles. So liquids are next. So they're only higher than solids, but they're less than gas and plasma. Particles are able to move around, and they're moving around freely. That's what gives it its nice flow. but they're still pretty close together, and they can't really leave each other very easily. They're still kind of connected. Well, they can leave if they spread out, pour it out into something. Same as you can break something, but that requires you to add some energy. All right, but then liquids have an indefinite shape, meaning they take the shape of whatever container they're on. However, their volume, the amount of space they take up, is always exactly the same. That's why we can measure volumes in milliliters. Now, if you pour water on the ground, it'll have the shape of the ground, won't it? It'll just look flat. So it has a lack of shape, so indefinite shape, but it will still be the same amount of water. That's its volume. Now, gases are the part where we start to get super high in kinetic energy, but just a little less than plasma. But it's probably the fastest that the whole particle itself can move around. And so they move around and they shoot around, and because they're moving around so freely and with so much kinetic energy, so much speed, that they have indefinite shapes, meaning they don't have a shape, and they don't even have a defined volume. Their volume is whatever container they're in. So if you have a poisonous gas in a jar and you break the jar, it's going to spread out to the entire room. That's why it can be deadly. So a deadly gas, even a small amount, could spread out to the entire room to where it could be deadly to everybody. Isn't that fun? It's also why when you pass gas and you hope no one looks at you, somebody starts to sniff and they're like, I don't know who did it. That's that gas moving all around the room. And fourthly, we have plasma. So it is the highest level of matter, or the highest level of energy in matter, and basically it's so charged that it's ripped itself apart. Think about almost like electricity. Think of lightning, things like that. It's not quite there, but even fire, it's a plasma. It's ripped apart to pieces, okay? No definite shape, no definite volume, meaning it doesn't have a shape or a volume. It can go anywhere. They're just super filled with energy, moving so far they can't even hold themselves together. This is just that breakdown. I'd shown this picture before. You can read about these here. Pause it if you want to. Now, you should all know that we're able to go through phase changes. Now, some of these are super easy. We know that going from a solid to a liquid is called melting, and going from a liquid to a solid, freezing, right? Not too hard for that one. You might not know that if it skips the stage of liquid, because we probably even know vaporization and condensation, going back and forth between a liquid and a gas, but skipping a stage and going from solid to gas, well, you would have sublimation, where it goes from a solid to a gas, and then you would have deposition. So that's where it goes from a gas to a solid. Now, there are some that are a little bit tricky here. Notice there is vaporization and evaporation. We think about these as the same thing, but they're not quite. Vaporization, so liquid to a gas, it happens at the boiling point. So you've added energy, it slowly got up there, and then it all starts to turn into that. Evaporation, liquid to gas, but it's below the boiling point. So if you have a large lake or ocean or something, that water ends up getting up into the air in our atmosphere, but it never reaches its boiling point. That's because it doesn't have to boil to get to that stage, that gas stage. It just has to have enough particles hit it on top that knock other particles free. And so you're only increasing the kinetic energy of small particles. So that's evaporation. Think about that happening out of things like large bodies of water. Vaporization, that's really what happens when you're boiling water in a pot. Okay, and then we usually don't know a lot about plasma, so it's just been called ionization if it goes from a gas to a plasma. An ion just means having a charge, so it means it breaks itself apart to a charge. And then deionization, D meaning not, ionization, or ion meaning charge, so not charged, so it combines back and no longer has a charge, basically. So the last thing I want to talk about with phase change is probably something you're a little less familiar with. So there's certain points, melting point and boiling point, and that's not the part you don't know. But if we were to look at it as a graph and think about the time, and then we know temperature is a measure of the amount of energy it has, right? So notice that if we start to increase the energy into a solid, like a piece of ice, so we're getting it to the melting point. Once we get to the melting point, that energy tends to stay about the same until all of it is able to start to turn into a liquid. And so it stays at these melting points and boiling points for a while. And it would be the same thing if we were taking energy out or freezing it as you think of it. And so you would get that gas and it would get down to that area of condensation to where you want to start to turn from a gas to a liquid, and it would stay there until all of it starts to turn that thing. This becomes a very important principle because it's the idea that you have a melting point and a boiling point to where things are converting. All of the energy goes into converting it from one stage to another when it enters here. It doesn't change the actual movement of them until they actually get to that new change. And because of that, you have very distinct points. So if we're thinking about water, we know that it freezes at 32 degrees Fahrenheit, right? So that means if you have a bunch of water and you get it down to just about freezing, it's going to hit 32 and it's going to stay at that temperature of 32 degrees until it's a solid block of ice. Once it's solid ice, then it can get much, much colder as ice, but it can only be 32 degrees as it's changing into ice. The same thing if you ever want to test a thermometer you have, you get a boiling pot of water. Once that water is boiling, as long as you have boiling water in there, it will be at that boiling point. I think it's about 214 degrees Fahrenheit. Celsius, it's super easy. The melting point is 0 and Celsius, and 100 with boiling point. But anyway, it stays there and you can test it. Because of that, we call those sections the heat of fusion and heat of vaporization. And so it's the amount of energy to change all of a solid into a liquid is the heat of fusion. Some of the attractive forces of the particles are broken, and that's why it doesn't increase in temperature. Heat of vaporization is that boiling point, basically, and it's the amount of energy required to change all of a liquid into a gas. And it's that same idea of why it doesn't increase in temperature. You're breaking all of the different attractive forces between the particles, and so that's what the energy going into it does. It doesn't increase their movement, it breaks the different forces holding them together.